Now that we know a little bit about how moving electrical charges produce magnetic fields, we can compare two different kinds of magnets. One is the classic permanent magnet, has north pole at this end, south pole at the other end. Another classic permanent magnet is this little piece of the compass. The red is, again, the north pole. The white is the south pole. So the north pole of this magnet points toward the south pole of that magnet. These are both basically permanent magnets. Now you know that electrical charges, moving electrical charges, produce a magnetic field. And in fact, we can make a magnet with a north and a south pole just by having a loop of current. And so here's that picture right here. An electromagnet, battery, positive here, negative there. Electrons are going from the negative to the positive side. Then current, what we call I, we define as running from the positive side to the negative side. So that's through this loop. If you are looking from the left, then you can tell that in this loop right here that the electrons are running counterclockwise, and so the current is running clockwise. Because the current is running clockwise, the right-hand rule tells you that magnetic field points to the right in the center here, and it points to the left when you're outside. So it's the magnetic field lines would circle around like this. These little compasses, they kind of look like all around here, are basically magnetic field vectors, and they get dimmer and dimmer as the magnetic field gets weaker. So it's strongest pointing to the right here in the center. Now, if I go back to the bar magnet has a magnetic field that points to the right when you're over here on the right-hand side. I can even tell. Magnetic field points to the right when you're on the right-hand side. It circles around. By the time you're down here, it points to the left. And by the time you're back up here, it points to the right again. And same is true here. A loop of current, magnetic field points to the right on the left-hand side. It points to the left when you're down below it, and it points to the right when you're on the right-hand side. So this magnetic field has exactly the same shape as that magnetic field for a bar magnet. Since the north pole is on the right, we have to say that the north pole of this electromagnet is on the right, and the south pole of this electromagnet is on the left. Now there's just one loop here, and you probably know that usually use a coil of wire. You usually wind loop after loop after loop. So let's measure the magnetic field and see what the effect of different loops does. So right now the magnetic field right here in the center, we know it's pointing to the right. We can see that, and its magnitude is almost 28 Gauss. What if I put more loops? Twice as many loops, 2 loops now instead of 1, twice the field. Of course, each loop produces a field. They have the same current. I just add the 2 fields together. 3 loops, 3 times as big a field. 4 loops, 4 times as big a field. The reason you wind 500 loops is you want a field that's 500 times bigger. So that's the purpose, winding loop after loop after loop in a coil. So here we have it. Magnetic field, when you're close to the coil, is big. It's 200 Gauss. Magnetic field as you get farther away from the coil is smaller. 9, 10 Gauss around here. 1 Gauss around here. And somewhere around Earth's field out here by the time you get to the end. At this point we can now compare the 2 magnets, and the coil seems to have a magnetic field through the center, and then it comes around. So the coil pretty obviously doesn't have a starting point for the magnetic field. The field lines curl around and then they loop back to where they started. So there's no beginning and no ending. The bar magnet makes you feel like it has a beginning and an ending because the beginning is over here on the right and the lines loop around to the left. But if I show the field inside the magnet, You see what's going on. In fact, the magnetic field lines come into the south side, then go through the magnet, come back out the north and back again. So what does this mean to say they go through the magnet? Well, you probably know that if I break this magnet in half, it's made up of a north pole and a south pole. If I break this magnet in half, then suddenly there's a south pole down on this end, and the magnetic field will go in through that. If I break it up again, every piece has a north pole and a south pole. Now, that, oddly enough, can continue and continue and continue. In fact, if I pull apart all the electrons and all the protons, and all the neutrons, then every proton, every neutron, and every electron has a north pole and a south pole. Now, the protons and the neutrons are not really important, it turns out, for what goes on in here, but the electrons are. So how does an electron have a north pole and a south pole? Well, it's a charged particle. We know that it has an angular momentum, and that means its charge is going around in a circle if it's spinning. And that tells us that the electron has its own loop of current. So that's how the electron has a north pole and a south pole. And in a permanent magnet, what happens is that you stack up a whole bunch of electrons, and for quantum mechanical reasons that are very well understood, in some materials there are a group of electrons that point in the same direction at low temperatures. If they all point in the same direction, that's like this entire thing having a bunch of north pole and south pole magnets distributed throughout it, with all the north poles pointing to the right, all the south poles pointing to the left. That's what a whole bunch of the electrons inside here do. So that's why there's a magnetic field inside here also. It's the field that goes from electron to electron to electron and then back out again.